So now we have a nice definition of period and frequency, and we know that a restoring force drives the system. We can go on to describe simple harmonic motion. Consider this classic example of a simple harmonic oscillator, a mass, actually a toy mouse, on a spring. So how can we describe the periodic movement if we pull the mouse down and let it bounce back and forth? What do we know about this system? What do we want to know about this system? Well, knowing where things are in space is pretty important, and knowing where things are as a function of time is a great place to start. So putting this in physical terms, what we can ask is, what is the position x of the mouse at time t? This is often written as the function x of t. So let's look at what we know and what we can do to solve for x of t. Well, firstly, we know quite a bit about the forces involved in our system. We know that if we extend the mass on the spring some distance x, then the force will be pulling back on the mass, and that force equals to minus kx. And we have a fundamental definition of force from Newton's second law, is that force equals mass times acceleration. So we know that F equals minus kx and F equals ma. So we have two equations that both equal force, therefore we can write that minus kx equals ma. Now you might be thinking that this doesn't really help too much, that we're looking for a relation that tells us the position x at any time t. And another way to say this is we want to know if we can plonk in a value of t, say 3.4 seconds, and calculate a number for x. But at the moment all we've got is minus kx equals ma, and we don't know anything about a, the acceleration. But you may recall from mechanics that we can find acceleration if we know position. Remember that a, acceleration, equals the rate of change of velocity v, and v equals the rate of change of position x. Therefore, if we find a function of x of t, we have a of t. We can write that acceleration as a function of time equals d squared x on dt squared. Therefore, we can write that minus kx equals m d squared x over dt squared. Rate of change is one way of saying taking the derivative, which is the mathematical term for this concept. Now, this course doesn't require you to know calculus, and that's exactly what this is. And I just want to say that you don't have to be able to do the maths here. But what I am showing you here is so core to what physicists do. We take what we know and then we try to extend it into new situations, make some assumptions, and try to explain what's going on, that I feel it's really important that we go through the steps here. Moreover, this is really great because you already know the two force equations involved. F equals minus kx and F equals ma. They are lovely simple equations, and now you'll be able to appreciate just how far we can go with these seemingly simple ideas. So what we have written down here is a differential equation. This is a mathematical equation that relates some function with its derivatives. And the solution to this won't just be a number, so the solution will be some type of other mathematical relation. If we look at the mass on the spring, we can see if we can gain some type of physical insight into the solution of x as a function of t. This will help us guess the answer to this relationship. We can then sub it back into the equation and check if it's actually correct. And actually this is how many of these equations are solved, so it's not really cheating. We're using our physical insight to guess the answer to the equation. So let's look at finding an equation of x that fits what's happening for our bouncing mass on the spring. Here's a series of pictures of the mouse. Let's plot this so we have a position axis here, this is our x, and a time axis here. At the first position here, the spring is the most compressed, and our mouse is at position A. We can add an A on the axes. The mouse is moving down in the next position, and in the middle position, the mouse is now at position minus A, which has a maximum spring extension. In the next picture, the mouse is moving back up, and in the final snap, the mouse is back at position A. If we now consider the velocity of the mouse, we know that the velocity will be 0 at various points in this plot. We know the mouse will have a zero velocity when it's changing directions at the bottom and at the top of its oscillations. So that means here, here, and here, the velocity will be zero. At the other two positions, the mouse is zooming through the middle of A and minus A, and here, the mouse will be travelling at its fastest. One final point to note here is that the acceleration is clearly not constant, as it would be in the case if the mouse was just freely falling under gravity. Indeed, in this problem, acceleration must be changing direction throughout this cycle. This means we can't just solve this like we could with the cannonball falling using the kinematic equations, as they are only valid for constant values of acceleration. We need a more complex solution. Let's add another full cycle of progression to the mice and see if this becomes more obvious. Axes again. Let's mark the position and the time axes. And remember, the aim of this exercise is to find x as a function of t. And once we write this down, we can then use that to find v of t and a of t, acceleration. Let's use our noses, or rather the position of the noses of the mouse, as a function of time and plot out what we see. We should be able to see the start of this solution. Let's connect the dots of the noses and what we know on the axes. So this looks a lot like the trigonometric function cosine, and indeed it is. It's a bit hard to see in this example, so I'll draw another cos function up here to make it more obvious. I'll draw it from a to minus a with a period of t, and I'll draw two complete cycles. So you can see that x of t is indeed a cosine function.